Good afternoon, packaging people. We are on lecture 11, so we're now in the middle of chapter 4. We're talking about container selection. We're continuing from yesterday. I want to today go through the homework for the week so people have more time to look at it and think about it. And then I'll keep going through the chapter. But I did want to run through some of the homework questions first. And hopefully that will spur some answers or spark some answers from people or questions. You can always send me a note, email me. If you ever want to jump on to one of these recordings, they're generally Tuesday, Wednesday, and Thursdays from 2 to 4 p.m. Oh, also, I want to mention tomorrow I'm not live recording. So tomorrow I'm just going to record it. So Brandon, you get 2 hours of your life back tomorrow. But generally, if someone wants to jump on, they can jump on anytime between 2 and 4 and ask a question, as well as Fridays from 4 to 5 p.m. Those are the office hours. I want to catch you all before happy hour, before you get too happy. So that's really it. But if you can always reach out to me. I've been trying to answer emails when I see them, and hopefully I'm answering the questions. It seems like I am, because I'm seeing correct answers on the homework when the people are asking questions. So everyone's asking really good questions, and I'm excited to see what you guys do for this one. Okay, so let's start. I'm going to start yesterday. I'm going to share my screen. So, okay, which screen can you see?
I can see both of them, the homework and the notes.
Okay, so you're seeing where it says packaging 450, chapter 4.
Yep.
And then you see the dunnage.
Mm-hmm.
Okay, you don't see all my emails and stuff up on the other screen.
No.
Okay, good. All right, so yesterday I'm going to go back over chapter 4. We went through the wonderful decision charts. So they seem convoluted, but once you actually start working with these, and if you have a pack and you have a part, I mentioned you should always have at least one part that is in production intent. That means that it's going to be as close to what's going to be in production as possible. Even if it's a prototype, you want to get the size right when you're doing the fit checks. Another thing is, if you can get more than one part, that's always great. If you can fill up an entire pack, that's always wonderful. Sometimes that's really hard because many times they don't have many sample parts and they don't want to give them away. They think that you're going to take them, literally put them in a box and break the box and break all the parts. And many times I have to assure them that even if I use the same part or parts for packaging testing, it is to confirm that the packaging works. So the goal is to confirm that the packaging protects. It's not to break anything, and that they will get functional parts back 99% of the time. I literally, throughout 30 plus years of working on packaging, I can't even think of a time that I received packaging samples, put it through any sort of testing, and the part came back broken. Not even computer packaging or electronics or anything like that. So again, it's really important to have those parts. So we talked about this decision chart, how once you have the part and you're plugging things in, you go through each one of the steps and just follow the flow chart. It will really help you come up with the best pack. Again, with both of these decision charts, the assumption is you're looking at the smallest returnable packaging you can use, which would start off with a handheld less than 30 pounds. If you can't get enough parts to fit because you're driven by the weight of the pack, especially if it's a handheld, and you're also driven by how many parts you can get in to that pack, because that will tie directly into those delivery routes and delivery times. So those are really the fit, how many parts fit, how, does it match that tack time, and does it meet the weight requirements? Once you get past that, then you're really looking at, you know, how the parts are protected. So again, that fit goes back into kind of where we ended up yesterday, where we were talking about the dunnage for this radio. So you have to add a separation between those parts to make sure the dunnage fits. First, you want a separation between the parts so the parts don't hit each other. But the dunnage is not only separating it, but it may act as a cushion as needed, depending on what it is. It could act in terms of like um, dissipating static discharge, electrostatic discharge. So there are many reasons why you might have the dunnage. So once you have that, once you have picked out your pack, you make sure that your dunnage and your parts fit in there together. And that was what this exercise was, that we looked at. So we had different totes. I talked about how you can calculate the weight of an entire unit load or whole full pallet load of returnable packaging with parts, with the top cap and the pallet and everything. So we talked about that. You can use these charts that are in here. One thing that I did not do, but I'm going to do, is pull up. Orbis has a PDF of their catalog. I'm going to put that in the supplemental data. It changes a little bit over time, but it's pretty accurate. The containers are standard sizes. The standards don't really change a whole lot. They do not only automotive packaging, but they do some other industrial type packaging. So once I put that in the supplemental information, which would be a great reference for anyone that's working in or going to work in automotive packaging. I will, direct you like which pages you should look at, because those are the ones that have those standard automotive containers that fit on the 48 by 45 pallets. So for your homework, you'll be using these charts quite a bit. And then this example of the dunnage. I hope this made sense. But basically, look at this as you have the thickness of your corrugated that is separating your parts. The radio is going to be fitting in those. You have those in the cell. And in order to do that, to do your kind of quick calculation, what you're going to do is you're going to look at the length, at the thickness of the corrugated to get to your part length. So even though this is 10.12 inches here, you're going to add the thickness of the corrugated, and that's going to give you 10.37. Same thing with the width and the height. You're taking the product dimensions, adding in the thickness of the dunnage. And that tells you like how much material you need, which is good to know for a couple reasons, because you get to see, how much material you're using. When this gets quoted, you can have a good idea already of how much material is going to be quoted. And then it also helps to understand what your dimensions are going to be, and to confirm that your part and your dunnage fits into that container. Which sometimes, every once in a while, it might show up that maybe you can't fit the part and the dunnage in there. Once you start determining, how much protection your part needs, you may have to back off a couple pieces. And sometimes you can go up. I have an example of a supplier, or sorry, one of my vendors, or one of my customers, I'm sorry, they're looking at putting things in trays. And I think I mentioned it before. So one tray has 27 parts, another one is 8, another is 24. And their takt time is 60 seconds. So I suggested that they try the tray that has 27 parts. Is there any way they can increase that to 30 and still fit in their tray? So that now they're pulling 2 trays per hour instead of, with 2 we're pulling 3 trays. They're only pulling a few parts from the last one. So their delivery routes are not going to be even. They're going to deliver, they're going to have an over delivery at some point. And then for those parts, they're all going to go in the same size tray. But now some they're going to be delivering, 3 an hour. Other ones they would be delivering 8 an hour. They'll have leftovers. Another one they'll be delivering, 3 times an hour, and they'll have even more leftover than the one that has 27. So they just don't match up. So, those are all the things that you're keeping in mind. Again, here this says combining the part and that dunnage to get effective sizes and weights gives you, like I said, this is kind of a quick calculation because you've already put that in there, and you don't have to, now when you do it, will my parts fit in here with this dunnage. It's a good second way to check and just make sure that you're not overfilling the bin or even underfilling it. So again, they're looking at, instead of how do I fit this part that has dimensions of 7.72 by 10.12 by 2.68, now when they're loading it in to their container, they're now looking at essentially a 10.37 times just under 8, 7.97 by 2.93, which is just under 3. So, it's can make a difference in, what they're using. So for this one, in this scenario, they're using RollPac bins and Orbis totes last because this part is big enough that, let's say you want to put this in one of these totes, for example. Let's say you want to put it in the 48.8, I'm sorry, the 48 by 22.5 by 7.3. Your ID is going to be here with this just under 45.5 by 20.5 by 6.3. So look at this radio. Let's just start with the 6.3 dimension, your height. Your height of your tote is 6 1/4, basically. So when you look at this, this is taller. Both of these dimensions are taller. So if you were to put that radio in, say this is your radio, let's say you put the radio in this way, it's going to be taller than the bin. It's going to be 3.5 inches taller. If you try to put the radio in this way and turn it so that now you're putting it in so that you have the length of that, and then you put it, say, this way, now you're still an inch over your bin. And if you do the 2.68, which is going to be, let's say, the thickness of this, then you're going to stack, you aren't even going to be able to stack 3 high, you're going to stack 2 high. And then when you look at that, is that really going to be the way you want to present that? Because now you're going too high from the bottom. Now you're going to have a layer of radios underneath the top layer. So that's not necessarily an option for dunnage for a bin. These are all 6.3. This one is 3.8 for the inside dimension. That means you'll be getting 1 high. So let's look at this one. So if you put this radio in, you're going to put it, you would have to put it in this way. So that dimension, the 2.68 dimension here would go into the bin, and this bin is 9.4 by 13. So if you got 9.4 by 13, that means that you're basically going to get 1 radio in this bin, because this one, you can't get this in the 9.4 dimension. So you're going to have to put this in that 13-inch dimension, right? Which means that 9.4-inch dimension is going to be taken up by that 7.72 inches. So when you orient that in that bin, that's you're going to only fit one radio in there. And if you use these bins, that 6.3 means you're going to be stacking one radio on top of the other. That's not ideal for the operator. It could cause damage. It would be really hard to create dunnage. When you look at the dunnage here, this dunnage, you have cells and you're pulling that dunnage out. You might be pulling that radio out of the dunnage and then inserting it. So it's positioned in a way, or maybe it's in a RoPac bin that's a custom bin. So they're able to pull those radios out right in, directly in front of them without bending or turning or anything. So they are it's only going to be one layer, basically, based on how they're probably going to load into the vehicle. Let's see. So I hope that explains, why this is going with the RoPacs. So, we talk about assuming that you're going to try to use a handheld tote first, but as you can see, this radio just doesn't fit in there. And it doesn't make sense to have one radio per bin. Let's say these volumes of, I don't know what vehicle this is, but let's just say the volume they might be making. Let's say they're making 1,000 trucks per day, like we saw in the Rouge video. They're going to need 1,000 of these bins for one day. And when we get into calculating the fleet or the number of containers you need for returnables, you need to know how many days worth of material are going to be in the distribution cycle at any time. So if let's say these radios are coming from, 200 miles away, and it takes a couple days to build them. So you're going to basically have to have however many days, let's just say 7 days of material times 1,000 per day. So now you're up to 7,000 totes just for this one radio. Versus with the RoPac, you can get more parts in there. So that's kind of where this is taking you as far as the using why the RoPac bins are going to be used. And they're using those. Okay, so here it's saying the totes will be used. So in this assumption, they're taking the form of dividers that separate the parts. So I've not really seen that before. I guess you could do that, where you could have a big RoPac bin and then you put handheld totes inside of it. It could act as dunnage because it's separating the parts. You could double stack them and not worry about the radios getting damaged, but I probably wouldn't do that. Okay, so again, we talked about how the dunnage can affect how many parts fit in there. And okay, so now let's see, we are looking at RoPac bins. So this talks about all the different ways. So when I showed you pretending this is a radio and putting in different orientations. So this would be one, this would be two, this would be three, this would be four, this would be five, and this would be six. So that's basically what we're talking about. How do you want to see how many parts you can get in. So it talks about, lining them up in the same direction, which I mentioned before, because the operator repetition is their friend. So if they're pulling the part out, the same orientation every time, they pull it out and stick it into the vehicle. So even if they pull it out and it's not oriented exactly the way they want to orient it, and they need to turn it or move it, at least they're doing that for every single part. So it's a repetitive motion. So that's why it talks about lining up all of your parts in the same direction. I mentioned you have this, 6 different ways you can do it. So you get 6 choices. And I kind of did this already when I talked about the small handheld tote, where I said, if you take this, pretend it's a radio, and turn it different directions, now you're getting, one per that one handheld tote, or you'd have to put them too high, which is not ideal. So this is talking about the different orientations. So you got orientation 1, 2, 3, 4, 5, 6. So that coincides with the 1, 2, 3, 4, 5, 6. And we're looking at that same table for those roll pack bins that we talked about earlier, which is going to be this table here. And notice of the weight capacities. I think these radials are pretty lightweight, so you don't have to worry about that for the radials. But if you have heavier parts, you definitely want to keep in mind what the part weights are. So are they going to max out the weight capacities or over capacity? Are they going to be over capacity? So now we're looking at these three bins. This is the dimension. These are the dimensions that we're focused on right here. Our bin inside dimension. If I can get it to, okay. So let's pretend I just highlighted this one row. This bin inside dimension. These are the three that we're looking at. The one that is that 80-inch outside dimension, which is basically going to be almost the size of two of these bins. So I think next time I teach this class, I'm probably going to take a picture of myself standing next to some of these roll packs so you can see how big they really are. Then the next one is going to be one that is this one, the standard 48 by 45 and 48 inches tall, which is basically going to be double stacked in the trailer. And then the third one is the one that I like to call the baby roll pack because it's a little, almost like a cube. It's very close to a cube. And those with the height of 25 inches, those could be stacked 4 high in a trailer on a truck. So just keep those things in mind as we go through this exercise. So remember, this is accounting for the length or the thickness of the dunnage, I should say. So again, we're accommodating the thickness of the corrugated, the 1/4 inch thickness for the corrugated. So keep that in mind when you look at these and these dimensions. Okay, so let's start with orientation number 1. Since the length is aligned with the length of the part is aligned with the length of the bin, you're looking at taking this and orienting it the same way as the bin. So they took the 76.5, which is the length of this bin, and that width is 44.5, and then the height is 26.5. So they took that and they said the bin length divided by the part length. So that's the 76.5 that I just showed you divided by the 10.37, which is this dimension that we added earlier that has the thickness of the corrugated. So again, you're going to take that bin length divided by the part length to get 76.5 divided by 10.37. That's going to equal 7.38 in total number of parts you could get in that orientation for that particular dimension. Now, you know, you're not going to be able to get a fraction of a radial in there, so you just round down. So now you're at 7. And then this one, so for this one, they basically took the longest part of the part, the longest part of the bin, the width and the height, and just lined it up that way. So then again, so we look at the width of the part and the width of the bin, and you're going to get the 44.5 divided by 7.97, which again, the number 1, 44.5, right? And then 7.97. which is going to be this plus the thickness of that corrugated board. And that is how they came to this part width. So, and then you're going to do the same thing for the height. So you take the bin height divided by the part height. And you get 26.5 divided by 2.93 equals 9.04. So again, both of these, you're rounding down because you're not going to have a partial radio. So you just round down. So here you've got 7 parts along the length. You've got 5 parts along the width. And then here, you're going to have 9 parts in the height. So you get the 7 by 5, 35 times 9 high is going to equal 315. So according to this, you can get 315 of these into a roll pack bin. Okay. So you'll do the same thing with the other ones. That's how they got these numbers. So you can see what the orientation was. You get the 315. You can do the same thing with all the different orientations, and you do the same thing with all 3 bins. And you can see the difference here. This one you get 315. This one, okay, this one looks like you get the most at 324, right? Roll pack bin number 1 with the parts and orientation number 2. You're going to get 324 of the radios into a roll pack if you put them in to the bin in this orientation. Okay, however, let's see. Okay, so this says that for bin number 1, orientation 2 is the best. That's what we have. Now, earlier, they did do a calculation called the liquid cube, which would be, you know, how many could just pack as many as you can in the box, and came up with 372. So you can see the difference that the dunnage makes. Go to that. Okay, I don't see it in here, but basically you do the same thing. Okay, here it is. I knew I saw it somewhere. Okay, so this one, they took the bin length of 76.5, the width of 44.5, and the height of 26.5. And then they divided it by the dimensions that we have here. Wait, the 10.37, 7.97, 2.93 again. So, you know, you take that, and that's saying that you can get that many, but we already know that that's the best case scenario. And you can see once you start calculating, you have partial, you know, you have part of a radio that won't fit in. So that's when you start losing some of that. Okay, so when you look at bin number 2 and you do the calculations, you see you can get 300. So still better than the third one, obviously, but not as good as your liquid cube of 372. So again, 372 is like you're trying to see how close can I get to that, because you know that things like the dunnage and, you know, things get partial parts and they just won't fit. So you're going to start taking off, shaving down some of those numbers. And then here you can see you have, you know, 27 parts as the max. And this one, when they did the liquid cube for this one, they saw was 37. So they have, you know, 37 versus 27. 315 was the max for that liquid cube versus 300. And then you got the 372 versus a 324. So you can see in each case you get significantly less. Now, I mentioned before, the other thing is, once you started picking your bin, you figured out that you aren't going to be using your handheld, now you're using a roll pack. Now, instead of looking at, what's the capacity based on what someone can carry, now you're looking at what's the capacity based on the strength of this container. And so now you have to start calculating the weight of the product in these bins. So for the first one, you can take that max, which was the 324 right here, and you will take, I'm trying to see if I get this, 2.63, which was the weight of the parts plus the dunnage to get 853 pounds. So for number 2, you do the same thing. You take that max, the high number, 300 times the 2.63 to get 789 pounds. So you'll see the weight capacity of this bin, number 2, is 1,500 pounds. So you're right now, for bin number 1, you're below the 2,000 pound weight capacity. For bin number 2, you're below the 1,500 pound weight capacity. And then for number 3, when you calculate this, you get 27 parts, it's going to weigh 71 pounds, right? So, you're definitely under that 1,000 weight capacity here. So you don't have to do anything, but let's just say that this radio weighed twice as much. We'll just say it's twice as much. Now you're, instead of being around just under 800 pounds, you're at almost 1,600 pounds. And that's going to go over that weight capacity. So then you start backing up to say, can I put fewer in, or maybe that's just not the bin I'm going to use. Okay, so then, you talk about how many bins can fit in the trailer. This is saying that the bins are done, you do this by using orientation. But again, because these are standards, it's kind of already known. So it's good to do the calculations so you understand how they come up with those. But when you're working in the real world with this, if you're working with Orbis bins, roll pack bins, they're going to be standard, and the supply chain team will already know how many fit on a trailer because you'll supply that information to them. The only exceptions from these standards are going to be, let's say you have a custom bin or a tote. And sometimes you can have a custom bin or tote that is not only customized inside with the dunnage, but sometimes you might actually change the length of it for whatever reason. Try to avoid that when possible, but it does happen from time to time. Okay, so how do you figure out how many bins will fit in the trailer? So now you're just taking your bin, and your bin is basically what you just did with the part, and your trailer is going to be what you just did with the bin from an equation standpoint. But also keep in mind that instead of using the inside dimensions of the bin that you used to see how many parts fit, now you have to use the outside dimensions. So let's look at bin 1 again. So bin 1, when we were calculating the liquid cube and calculating how many parts would fit in a bin, we used the inside dimension. Which is this, right? So for bin 1, it was 76.5 by 44.5 by 26.5. However, now that we're taking the bin, and when we went to see how many parts we were fitting in, we used the absolute largest size, including the thickness for the dunnage. So we were using the outside dimensions for what was going into that bin. Now we're taking the bin, we're using the outside dimension because that's the worst case, that's the biggest scenario. And then we want to see how much fits into the interior of the trailer, which was part of one of the exercises in homework assignment number 1, where we're measuring, the square footage and trying to determine how much space is taken up in the trailer. So for this, you're going to take the inside dimensions of the trailer. So We'll go back down here. And so that's what we're doing. That's why you see this. So you've got your dimensions of 98.5, 630 inches, and 106 inches, right? And then you're taking the outside dimensions of these bins. So your bin length is the 80. So again, we're back at the outside dimension of that bin, which is 80. The bin width is going to be the 48 and the bin height is 34. And those again are the outside dimensions. So you're looking at the different orientations, which you're going to line up with the length of the trailer, the width of the trailer, and the height of the trailer bin with the bin. So you do the same thing that you did before. So you're going to take the length of 630 and divide it by 80, which is the length of the bin. So 630 inches divided by 80 inches. So as you can see, this is all converted to inches. And then you come up with the 7.88. Again, you're not going to get a partial bin on the trailer, so you just round it down to 7. And then you do the same thing with the other one where you're taking this bin and turning it on its side. So again, since this is the 80-inch bin, I see why they're doing this, because if you're using one of the other roll packs, it fits a certain way in the trailer and you know automatically how many you have. But since this is an extra long bin, it's 80 inches, you want to see how many fit in this dimension versus how many fit along this dimension. So this one, you're lining it up this way and you can see the 7, 1, 2, 3, 4, 5, 6, 7. So this is how you get this 630 inches divided by the 80 inches of the bin to get 7.88. And you know, you're gonna have some extra room on the trailer after you put the 7 in here, but the 8th one will not fit. So that's how they come up with that. Then the next one you're gonna take is the 98.5 and divide that by 48. So you're gonna take this dimension, which is the width of the trailer, divided by the width of the box. And you get 2.05. So this is telling you that you can get 2 in here in this dimension, in this direction. And then the third one is taking that height, the 106, to the height of the trailer, and then dividing it by 34. And you get 3.12. Again, you round that down to 3. So that's where you see 7 times 2 times 3. And when you add these all up, you say 7 times 2 times 3, you get 42. So that's how you know 42 will fit on the trailer. You could try it again with the other orientations and the other bins to see. So here you see that for bin number 1, you get either 42 or 39, depending on the orientation, right? This one, interestingly enough, this one is that standard roll pack bin that I've been showing you all the way through. And we talk about 52. That is the orientation that everyone uses for the most part. But you see, if you turn that bin on its side to, you know, turn it to a different orientation like this, now you're actually able to get 56 in the trailer. Interesting. And then with the other one, that's small 30 by 32, the baby roll pack, you can either get 228 or 252. Okay, so for bin 1, you're gonna get the maximum number of bins and part radials in orientation number 1. And you calculate that by saying, you know, you get 42, which was, you know, the 7 times 3 times 2. You get 42 of these bins on a truck. And then we calculated earlier that you can get 324 parts in that orientation. So that's where they came up with this. So you have this 42 times the 324. And that's according to this, if you use the large bin and you put the parts in orientation number 2, you will get in this orientation, you can get 13,608 radios on a trailer. Okay. Now you know that, again, now you want to check the weight of the trailer. Like I said, these are pretty lightweight, so I don't anticipate this would be an issue. But if you're using heavier parts, you still want to check this. So now you know that the filled bin, we calculated the parts plus the dunnage to be 853 pounds, right? Then we also know from that table that the weight of the bin from this table, that bin is 290 pounds. So then what you come up with is 1,143 pounds. So that is the weight of one bin with parts and dunnage and the weight of the bin. It comes up to 1,143 pounds. Again, okay, so it is going to be too much. So the weight so you know you have 42 bins per trailer times 1,143 pounds. So you're going to, it comes out to 48,000 pounds, just a little bit over 48,000 pounds. But remember, again, we talked about that 45,000 pound weight limit of parts or anything that you're putting on the trailer, the loaded trailer, and it's going to make it exceed the weight limit. So now this is telling you that you can only get 39 bins on there. So that would take you back to this orientation. And the way they got to that was they took the 40, they went backwards. They took the 45,000 pounds, which is a maximum number, the maximum weight you can put on the trailer, and they divided it by 1,143. And then 1,143 again is weight of one bin with parts and dunnage total. So they backed into it that way to say, okay, I can't do more than 45,000 pounds. I know each bin weighs 1,143 pounds. So what's the max number of bins I can get on this? So it's 39.4. Can have a partial bin. So you're down to 39 bins. So it's going to actually bring you a little bit below the 45,000 pounds. So let's look at this here. So let's just say 39 bins. So we can kind of do what they did up here, times the 1,143, because that's the weight of each bin. So we know for this, let's say we're looking at this orientation, 39, and multiply 39 bins per trailer times 1,143 pounds per bin, and we get 44,577. So we're under the 45,000 pound weight limit. Barely, we made it. So this is saying, you know, since it's the same for orientation number 2, we'll just go ahead and use that, because we already know that orientation, you know, that if it's in the trailer, that it's probably going to be a little bit more stable. Because if you're, let's say with this, the orientation of 42, and you're going to take 3 off to get to 39, if you're trying to do this orientation, you're going to have to either take off a stack of 3. So now you're going to have a big gap here, or maybe take off 1, 2, and then a third one here. So it's going to be, you have an unstable box here. So it's really better if you just turn everything so you have even stacks. That's how they came up with that. So even though this has the highest number of parts per truck, it goes overweight. So you can't really do that. Okay. So then they do the same thing for bin 2. And again, they looked at that. Orientation 2 was the best for 56. They calculated parts per trailer. They knew the weight of the bin, and it comes out to 964 pounds. This one is now 53,000 pounds, just under 54,000 pounds. So again, now you're backing off, and you take the 45,000 divided by that weight that you have of the 964 pounds, which is the weight of the parts, the dunnage, and then plus another 175 pounds for the bin itself to get to that 964. So they took the 45,000 pounds max limit for the trailer, divided it by 964 to get the 46.7. Again, you round down, so you get 46 bins. When you look at this table, even though it shows 52 and 56, you're going to have, quite a bit fewer than that. And according to this, you can use either orientation, right? But again, when you start looking at loading the trailer, you want to make sure you're not having like uneven stacks or anything like that. So as you go through this exercise, you want to make sure that your loading pattern is something that the loaders can replicate over and over again. Okay, so then for bin number 3, the same thing. Orientation number 2 was the best at 252. And just to refresh your memory again, that was, looking at bin number 3 with 37 parts. Go through that whole exercise again and come up with the 252. So then what did they do again? Take the parts per truckload, which you have 27 parts, 27 bins times the 252 to get 6,804 parts per truck. Okay, so you know that your bin weight is 71 pounds for parts and dunnage, plus another 50 pounds for the bin itself. So it's 121 pounds. So you're going to take your 252 times the 121 pounds to get 30,000 pounds per trailer. So you're below the weight limit on that one. So you're not going to get as many parts with this one. It's underweight, under the weight limit. So you're good with that. But when you look at the 3 roll pack bins, you say number 2 works out well because you're going to get 13,000 parts per truckload versus the 1. So this one started out with 16, but because of the weight limit, you're now bringing it down to 13,000 parts versus the 6,000 parts. The other one, you ended up with 12,000 parts because of that weight limit. So you got the weight limit and the weight of the bins. So here's one other thing, the weight on the bottom part of the bin, right? So, you want to make sure that you don't have compression issues in those bins. So here it talks about in part orientation 1, it's vertical. The height of the part is vertical. So you're going to have 14 parts stacked on top of each other. And I talked about that earlier. So you want to make sure that even though the bin itself can withstand the weight of all those parts being compressed, remember, you are separating those parts with corrugated. You're not necessarily separating those parts with like a cloth material that would actually keep those parts separate and keep them from compressing against each other. So if you're putting a corrugated pad in there as a divider, those parts are basically compressing on each other. It's not a corrugated box where you have the corners and the strength of the box to, or even those dividers to hold it. So you want to look at that too. For this one, you've got 14 parts that are stacked on top of each other. So now you're taking your compression force for the bottom layer. You've got 14 stacked. You subtract the one because that bottom one isn't compressing on itself, and then you multiply it by the weight of the 2.63 to get 34.2 pounds. This is where you want to understand your part. You want to have a good relationship with the part engineers, and then just be confident that this weight, 34 pounds of compression force, does not damage the radio. So that's something you just always want to check and make sure of. And then another thing that I mentioned earlier is when you're having the routes and you're replenishing. So bin number 2, you can get 300 parts on there, excuse me. So going back to that Rouge plant where they're doing, say 72 cars per hour, you're taking the 300 parts per bin, dividing it by 72 per hour. So that gives you about a 4-hour supply. So that goes back to when we talk about replenishing, and you want to keep a few hours, couple hours, or more than 4 hours. So, this kind of goes along with that. So you're good there. So this just gives you an idea of all the things that you're checking. It seems like it's endless, but after a while, you just naturally start looking at it and everything falls into place. Okay, so you can do the same thing for the totes. If you want to do the calculations, see how it happened, you can see here when I talked about the totes earlier, I mentioned that one where and I showed you that example, was kind of on my phone and turning it, but I said you can only get one in there. And you see a lot of these show 0. You cannot get even one radio in there in those different orientations because the height of that bin is shorter than the height, whatever whatever dimension of the radio now becomes the height when you turn it in different directions. So again, this Orbis tote, this is not necessarily representative, but let's just say that this tote, that one tote, I think was what? It was 3.5 inches, 3.25 inches, but the radio itself, in this case, it would be that 2.6. So you'd be getting stacked 2 on it. This one, it's taller than the height of both of these instances. When it's placed in the bin this way, it's going to be sticking up. It's going to be taller than TH. So PH is taller than TH in 2 of these. So that's where you're seeing all these zeros here. And then that one scenario, which I think was this orientation, you're only going to get 1 in the bin. This one, you couldn't get 1 in the bin because it's going to be sticking out. It won't be taller, it won't be wider, but it will be longer. So that's where this table came from. So they basically went through the same exercise. I did it in my head, but they went through the same exercise, wrote it down, and put it on the table. So that's where all these come from. Okay, Brandon, any questions since I've gone over these charts for an hour?
No real questions. Really just in regards to the last thing you went over with the compression strength of the bottom box. Do the returnables have a safety factor, like in regards to the corrugate options when you got to do a safety factor for environmental hazards?
No, the bins do not really. When you're doing that, you're really looking at the dunnage. You're looking at what is the dunnage doing. So when you look at that, just pretend that the bin doesn't even exist when you're looking at your compression.
Okay, gotcha.
So that's why you're just looking at a pad or dividers, and that's it. You have dividers, and what is it doing? I think I have a Okay, I have an example here. This isn't not exactly the same, but this is a box that has dividers in it, right? And these parts are the parts that go in here, they're plastic parts and they weigh nothing. So you've got the divider here. They were able to stack too high in this. So they put a pad in here. So there's a pad in here. We'll do this. So here's the other side. Here's the other one. And then we've got that wonderful pad that doesn't want to cooperate. Okay, so then you've got inside of your, whether it's a corrugated box or whether it's a bin, you're going to have whatever compression strength. This is single wall corrugated, but in that one scenario, they're looking at 14 radios stacked on top of each other. And I don't even think they were even necessarily talking about a pad to separate them, but I would think that you probably would. But you're now looking at, what kind of compression does this take? And you can see the fluid direction on this is not really giving any strength. It's just acting as a divider. Your fluid strength is here, so your compression strength is going to be coming from here. But when you've got parts placed inside of this dunnage, for example, now the only thing that is breaking them up in between is going to be, if you have a pad, it would be some kind of a pad. Does that make sense?
Yeah, it makes sense.
Okay, great. All right, so this is going through the same exact scenario, but looking at totes. So we already know, the totes aren't going to hold anything, but showing you how to do it, you can go through all these different scenarios. So you want to do the liquid cube, 24 parts, and then you get 16 parts here, but your liquid cube was 24. So you already see that it's chopping it down. Same thing with this one. You had 11 parts max, but with your liquid cube, maximizing every square inch. But when you actually do it and you start, rounding down, you're going to get 8 parts. And the same thing with this one. You only have one orientation. We already talked about this. This is the part where you get one part in there. So that's really it. So, you can look at the different ones and say, okay, am I going to use a tote? Maybe, maybe not. If I do decide to use the tote for any reason, again, maybe why would I use a tote in this scenario? Because maybe there's not enough room on the line. Maybe the room that is slotted for radios is only enough for 1 hour or 2 hours of material right on the line. So those delivery drivers are going to be delivering on those routes, and they're not going to keep any excess material at the line. They're going to basically be feeding the line as they need them. So if they're doing that and they have limited space, they might actually only have set aside room on the line for totes. So if you notice when they had that video for the Rouge Ford plant that we watched, and I said, notice the packaging, you'll see some areas they had marked off for bins, some areas they had marked off for racks, and those flow racks, which were those modular racks that they could put boxes or bins on, and they would slide towards the operator, and then when the operator emptied it, he could take the empty pack and put it at the bottom, and then it had gravity feed to go back out towards the people doing pickups with their tuggers or their trailers or their fork trucks or whatever they might use to pick it up. So you might use totes if you have limited space on the line or just limited space in your plant for whatever reason. So they may have a dedicated spot only for totes. So let's just say that's why they're doing this. So now you're looking at totes because there's just not room for this 80-inch roll pack on the floor, or even a 30 by 32, for example. So for this one, it shows you as you do all your calculations, it says orientation 1 is the best. You get 8. So you can do 16 parts versus 8 versus 1. So your next thing is, now there's a handheld tote. You already looked at, there's those big bins that they weigh out the truck, that they go over the capacity of the weight limit of the bin. Now your limitation for weight on this handheld totes is going to be your ergonomic limit for a manual carry of 30 pounds. So when you look at these, for tote number 1, when you take those 16 parts by the 2.3 pounds, you're going to get, and then you add the 9.8 for the tote itself, you're going to come up with 51 pounds, just under 52 pounds. So, that's not going to happen with the handheld tote, because I'm not going to be on the floor carrying a 50-pound box or 50-pound tote 700 times, or I don't know how many times a day. 50, 60, 70 times a day, however many times a day it's going to be. And then for tote 2, the filled weight, once you do this, is going to be 8 times 8 parts by the 2.63 pounds, including the parts, and then another 6.3 pounds for the tote. You come up with 27.3 pounds. So technically, tote number 2 could be used because it's less than 30 pounds. Keep in mind, some of the plants, even though they say 30 is their limit, they may push back on some of these items for 25 pounds. So just be aware of what your plant can do. But in this case, we're looking at 30 pounds as a limit. And then for tote number 3, the same thing. You've got that one part multiplied by its weight of 2.63 plus 2.2 pounds for the tote itself. So you're coming up with 4.8 pounds, 4.83 pounds for a full tote 3, for someone to carry that one radio in that small tote by itself. It's going to be just under 5 pounds. Okay, so now we're doing the same exercise because now we know for whatever reason, we've been pushed to using totes. So now we know our options are either tote 2 or tote 3, because tote 1 is going to be too heavy at 50 pounds. So this is where we start talking about the standards for these totes. So these totes fit on the 48 by 45 automotive pallet, and their standard setups or how many fit on a pallet, like we talked about before, where if it's a 48-inch long one or 24-inch long one, whatever it is, it's going to be divisible by that 48-inch dimension. And then the other end of the other side of the tote will be divisible by the 45-inch dimension. So you might see, 15 or 45, anything that's going along in that one. This one you might see, 12, 24, 48 for the totes dimensions on that side. And that is so that they fit on these pallets. We already know that on those pallets, we can get 13 in a trailer, and you can see how they did that. So we've got the 48 by 45 footprint, and most people just say 48 by 45. So, most people don't really use that 0.8, but that's the actual dimension. So, okay, so only totes 2 and 3 can be used again. And that was based on the ergonomic limits. So the unit loads for 2 and 3, you can find that on the table. Unit loads 2 and 3. Let's go back to that table again with our bins. So you'll see you'll be using this quite a bit. So these are our totes, and you can see the outside dimension is 46.6, 46.8, or 43.2. That's what that is. That is the outside dimension, the height of each bin. So that's where that came from. So, so you know that that's how we know what that height is. You can see those can be stacked too high in a trailer, because if you're going to 46.8 times 2, that's going to be less than 110. Let's see. For this one's 106. So let's say the 106. So I want to make sure I'm clearly spelling this out for you all so you all can see it. Okay, so that's how you determine they're going to be too stacked too high in a trailer, because you're going to take that 46.8, 106 divided by 46.8, or 106 divided by 43.2, and then you're going to round down. So you can see here, you've got the, and then you've got the width of the trailer, so 98.5. They're dividing it by the 48.8 dimension, and see that they can get 2 across. And then you get the number of your unit loads to fit inside. It's going to be 2 across, 13 deep, and then 2 high. So that's going to equal 52. If you were to turn these loads around 90 degrees, now you're only going to get, you're not going to get that many in. So this is the maximum for this 4845 automotive footprint that you see for the main standard roll pack, as well as the pallets. You are going to get 52 in a trailer. So you probably heard me mention this before. That's where this comes from. Okay, so for tote number 2, so now again, we're back to totes 2 or 3, right? So for tote number 2, you can get 24 totes per unit load, basically on a pallet. So you look at that pallet pattern. And then that tote, we go back to that table, we see we get 8 parts per bin, or per tote, I should say. So go back there and you have the 8 parts per tote, 24 totes per unit load, and then you multiply it by 52, which is the number of pallet loads on the trailer. So that's how you calculate that you have 9,984 parts, just under 10,000 parts. So now that you know how many parts you're going to have on a trailer, you can take the, again, the weight of that unit load, parts plus the dunnage, and then you're going to add the weight of the totes, the pallets, and the cap, which is on that table that we looked at before. So you can take the 24 totes times 8 parts per tote times the 2.63, which is going to be the weight of that part, again, that we keep using. And then you add the 218.8, which is going to be the weight of all those totes, plus the pallet, plus the top cap that you use for that. And you come up to 723 pounds for each unit load, each pallet load of totes and parts and dunnage on that trailer. I'm sorry, on that tote, on that pallet. So then you're going to take that and multiply that by the 52 pallets that you have on the trailer. So that take that 723 that you just 723.8 that you just calculated, multiply it by 52 to see how many you have on a trailer. And that's the weight, which you come up to 37,638 pounds, I should say. So your weight of your parts is less than that 45,000 pound limit. So you're good. You're still good on that. So you can see what we've done is we've kind of gone through that decision tree as we're doing all these calculations and looking at, do I have a small tote? Do I have a large tote? With this one, they probably went through the decision tree and said, okay, we could use the bin. But then when they got to a certain point, they realized through their decision tree with the information they had, well, maybe we need to put totes on the line. So we go back to the original choice of using handheld totes when possible. Let's see. So, same thing with tote number 3. You've got 108 totes per pallet. This is it's a smaller tote. Again, tote number 3, remember, this is the one where you only have one part per tote. Okay, so you're basically going to get 108 totes per unit load, one part per tote, times the 52, because you know you can get 52 of these pallets on a truck. And that's going to give you your weight. First, you're going to have 506,016 parts per truckload. So you have just over 5,500 parts per truck. So if you put these in the bin where you can put one radio per bin, you can fit 5,616 of these radios on one truck. So then you want to go through that whole weight exercise and see how much does this truck weigh now. So you have the weight of that unit load, which again is that you get 108 of those totes on a pallet, one radio per tote, 2.63 pounds per radio, plus 307.6, which you get from the table, which is the weight of the totes, the pallets, and the cap. So that each pallet is going to weigh 592 pounds. So for each unit load or each fully loaded pallet with parts and totes, it's going to weigh 592 pounds, so just under 600 pounds. So for each of these 600 pounds pallets, you put them on the truck, you can fit 52 of them on a truck. So you take the 52 pallets, 52 pallet loads per truck, you have 52 spots on this truck, times that weight of 592 pounds, which is your fully loaded pallet, and you can get 30,784 pounds. So again, you're well under the weight limit. Okay, so if you're just looking at those totes, you can see you're really going towards number 2, because you're getting more per trailer. It's going to weigh 37,000 pounds versus 30,000 pounds, but you're going to get 9,000 parts per truckload versus 5,600 per truckload. So here you're getting almost 10,000 radios per truck. With this tote, putting one per tote, you're only going to get 5,600 parts, 5,600 radios per truckload. So that's kind of how you look at it. You've gone through all these exercises, weight, the size, think about limitations on the floor. You go through that decision chart, and now you've got it narrowed down to these 2 totes. And then when you start looking at how many do I get per truckload, you're looking at tote number 2, because like I said, you're getting almost 10,000 parts per truckload. You're almost doubling how many you're getting as far as radios per truckload. So you're shipping, you're using almost half the number of trucks, with the cost of freight, fuel, driver shortages, on and on and on. We talked earlier about the cost of a truckload, right? So you've got in here, and before about $800 was a standard cost per truck. But now we're looking anywhere from, $1,500 to $5,000, depending on what it is, what you've negotiated. So just imagine if you're putting, 10,000 on a truck, almost just under 10,000 radios on a truck versus 5,600, how many more trucks you're using and how fast that cost could add up over time. So, if you start doing this pretty regularly, you'll kind of be able to figure out, and you kind of know which ones are probably going to be the best. But you're basically going to be doing this type of calculation in your head, basically, or maybe on a spreadsheet. But it's really important to understand how this works, so you understand the process, understand how it flows into your decision charts. All right, 20 minutes of talking. Any questions, Brandon?
Nope, no questions.
Okay. All right. So let's see. I'm gonna save the improvements for tomorrow. We have quite a bit to go through, but I did want to go through this homework here. Because I think this is important. A lot of the stuff we probably haven't gone through yet, but I think it's important to go through um, these questions. So the first one, you're talking about, how many knockdown roll pack bins can you fit in the standard 53-foot trailer? So you again are going to your spec table. So see, we just got through 413, going through all those calculations. So this is telling you to go to 420 in your reading. Okay, and you can see here, this is, if you go to Orbis's website, or if you have an Orbis catalog, you'll see this as a typical type of table. So this is telling you a couple things. You got the height of the container. So we'll use the 48, 45, 50. I'll just use that one because it's a little bit more even. So we'll use this one as an example. So the height is 50 inches. So that's going to go along with, stacking 2 on a trailer. It's pretty easy calculation because you're going to be 100. So you kind of hit that rule of thumb, right? The dimensions, the exterior dimensions are the 48 by 45 by 50. So keep in mind when you're calculating, like how many go into a truck, you're using that exterior dimension. When you're trying to see how many parts fit inside the bin, now you're using the interior dimensions. So you see the difference, 48 versus 44.2 versus, times 41.2 by 43. So even though this is 50 inches tall, you're only going to get 43 inches worth of material from top to bottom. Notice that compared to the 45 by 48 one, even though there's 2 inch, this is where you get 2 inches of difference here too. But you can see there's like a 7-inch difference between the exterior and the interior. Part of that is the pallet. You can see the pallet here, basically the pallet base, and then you can see, the base of the bottom of this. And so you don't even start to have fill volume to be able to fill this until you get past this whole structure of where the pallets can be moved by fork. Okay, then you've got the collapsed height. So this is what you're looking for, 29 inches. So when you talk about the collapsed height, these roll packs or Orbis bins, they can fold down. So not only does this door open, but it will collapse down really small. So you can see it's 50 inches. When you collapse it, it's 29. So it's almost half the height of once it's collapsed. So remember, you're going to have the height of this base where the forks can still pick it up. All of this is going to fold down. So that door is going to fold down. Everything's going to fold down flat. And you can kind of see right here, this is where there's a hinge. And so there's a hinge here. So all of this folds down into itself. And now that bin is going to be about this tall once you're done, plus the height of the thickness of this wall. So that's how you get this plus the thickness of that wall, and that's going to give you the collapsed height of 29 inches. You've got the weight of that bin. Your internal volume is 45.5 cubic feet. To kind of talk about that liquid volume, it kind of tells you what that is. Your capacity here, you can see this is 1,700 pounds, you know, this is bigger than this one, the capacity is 2,000 pounds. So just keep those sorts of things in mind. You know, just make sure you have access to a chart like this. So when you start filling parts into your bins, you know what those weight capacities are. This tells you what your max loaded stack height is static. So this max height, so for this one, it's 4. So you could put 4 of these static, meaning that once they go to warehouse, you can stack them 4 high. And they should not fatigue. But you notice your dynamic height. Your dynamic stack height is when it's moving. So when a fork truck has picked these up and is actually moving these around, your stack, your loaded stack is not as high. So keep that in mind as well. You want to make sure that your maximum load for dynamic stacking, which means when your pallet load or your unit load is moving around, say by fork truck, you want to make sure that you are not going over that. So we know for this one, you can only get 2 in a trailer. So basically they're going to take these out of a trailer and they need to, when they move them to the line or move them to a warehouse space or move them to a supermarket, wherever they're going to move to after they take them out of a truck, they should not be more than 2 high when they're getting moved. So if you go into a warehouse, they take the 2 out of the trailer and then they pull 2 more out and stack 2 on top of them, and then the fork truck driver starts moving, they've already gone past their dynamic stack. So just those are things to know. This one, these all have 2 drop doors. So this is the drop door. When this door is closed, it looks very similar to this, but you can see there are hinges on it that you can open it with. But all these have 2 doors. Tells you what the door height is. So this is 21.8 inches high on both of these, all 3 of these. The width of the door is 33 inches. And that's good to know because if you have parts that are a certain size, you want to know, am I able to use this door to get them out? If you get parts that are larger, or with this one, you can see you have multiple stacks in here with the dunnage. So generally what you'll see is they're not going to reach all the way. Say if this is 50 inches tall, they're not going to reach in from the very top, reach all the way through the dunnage and try to grab the part out. They would pull out the dividers. This might have 2 or 3 pieces of dunnage in there. They will empty out all the dunnage here, take that piece of dunnage out, and then they will reach down into this. So let's say there are 3 pieces of dunnage in here, which it looks like there might be. They will empty out the first row, take that dunnage out, set it to the side. It gets saved because if this is returnable, it probably goes with returnable, or it might be attached, but it folds. So it will fold out of the way. Either way, the plan is that it goes back with the bin. And they take this one, empty the first row, empty the second row. They get to the third row, which is down here, but they can't reach it. So that's what the access door does. They can open that door and now they can reach down and pull those parts out much more easily. And they have 2 access doors, because when you saw the equipment for material handling and some of them had turntables, they could go on this side, empty the parts, turn that bin instead of reaching all the way across, because you can see it's like a 48-inch long or wide tote. So instead of reaching all the way over, now all they have to do is turn. They have it on a turntable. They can just turn it, pull those parts out. So that's what that access door is for. And then you can see what your fork opening is. This is good for people to know what type of fork trucks to have. If they have certain fork trucks, maybe certain bins won't work in their facility, or maybe they have to get the fork trucks modified, that kind of thing. And then you have the capacity in the trailer. It tells you the 52, which is what we just calculated. That's a standard. Or if you have a 53-foot trailer and they're collapsed, you can see now you can get 78 in. So where you get 52 of these full of parts, and not broken down. When you break them down, you can now get 78 parts per trailer. And the same thing for all of these. You could see on here, you get 52 for these because they have that same 48, 45, and they're stacked too high. But if you collapse them, now it's 27 inches versus 48, and you get 104. So, and that's what this is. So you'll need that for the first question. Let's see, for number 2, you are looking at the same radio, and we kind of went through some of these scenarios about how many of these, they're calling them CD players, how many can you fit into the roll pack for the 45, 48, 34 bin. So again, you're looking at this bin right here, 48, 45, 34. So now you're going to go through that same exact exercise that we went through earlier to see how many of the radios would fit in here. And you're using that same dunnage, that same thickness that we used before. So basically you're using all the same things, but instead of those bins that we use in the exercises, you're using this bin. It tells you already here you've been given, let me see. So you want to, you've been given that information. You want to start off by figuring out what the liquid cube is and look at, the orientation. So again, using the same CD player, how many players can you fit into the 48, 40, 45, 48, 34 bin? And that table is the one we're looking at on table 4, page 420. And you want to make sure they're all aligned the same way inside the bin. So looking at those orientations, those 6 orientation examples that we talked about earlier today. And then, like I said, you want to start off with your liquid cube to see, what would be the maximum. But knowing that you're gonna have to back out of that, you're gonna have to start, shaving off partial radios and partial bins and those sorts of things, to make sure you can get, everything into the trailer. And then you want to check things like the weight as well. Okay, so now the next one is in the Orbis table on page 4.6, which we looked at earlier. Then once you have that table, which was this table here, right? So in the Orbis table on page 4.6, how are the 12 totes in number 1 arranged in the unit load? Okay. So this one here is asking you, what does that pallet pattern look like? Like how many, how do they come up with 12? So, look at how many layers, how many totes per layer, how many layers go on a pallet for your unit load. So you basically are trying to figure out, how did they get to the 12? Number 4, what is combined weight of the pallet, the top cap and tie downs for a unit load of Orbis totes number 1? So we got Orbis tote number 1, and it's a 48 by 22 and a half by 7, right? So you're going to use that chart there. Let's see. So you are going to look at that same number one, and you want to figure out for the unit load, um, you know, what is the weight of the totes. So you just want to, you're looking at the pallet, the top cap, and the tie downs. Okay, so you're basically, you need to separate out the weight of the totes because you're just looking at the weight of the pallet, the top cap, and the tie downs from that total that you have. Okay, number 5, in the US auto industry, this is an interesting one because I had this conversation with one of my clients today. Who owns the returnable containers used to transport parts? The auto manufacturer, the supplier, or the trucking company? So this is something that we haven't really talked about. Well, I probably mentioned it, but it's further into your reading. But I can give you an example of a client of mine that they they did not understand the standards. When they brought me in, they had already made an agreement with their customer. And the customer, they'd made a decision on who owned what, and they don't have enough containers now because the party that decided that they should own the containers only bought containers for a certain part of the journey. So now there won't be enough parts for enough packaging for the entire journey. So yeah, that one, you don't want to read about that one. That is it's pretty standard. And it is, specifically for totes. And there are, other entities might own racks or things like that for WIP, which is the work in process. So you might have a bin. So, I think I talked earlier about how you might have the same parts, pink bin and the blue bin. Pink bin stays inside the plant. The blue bin gets transported between locations. The pink bin, they might be, putting this part together, and they might still need to add the label or print on it or something like that. So it's still being manufactured. So it's still in process. So, people might buy their own for that, but they don't plan to send those out and about. Let's see, number 6. A company finds that it needs a fleet size of 400 containers to satisfy its customers' demand for 250 containers per week. So we're now at the beginning of doing fleet calculations, and we'll go through this tomorrow. But how many days does a container spend traveling from the company to the customer back to the company? Assume the company has a 5-day work week. So you know that their fleet size is 400, when normally what you're doing is you're kind of going the other way and you're trying to figure out how many containers you have. So according to this, it's already been calculated. They know how many they needed. They have 400 containers. So they have 250 containers they're using per week. So what that means is if they didn't move them anywhere and they just kept them in the plant, they would be using 250 containers per week. So if they have 250 containers per week, they know that's what they're using. Why 400? Why did they buy more? So that tells you that, well, it takes time to build the parts. It also takes time to ship the parts. So it's all well and good if, let's say that, we're using one of these a day, right? but you empty this out, you use it during the day, and then it's got to go back to the supplier to fill it again with parts. So they use this up in a day, they send it back, but then the next day they don't have any containers, they don't have any parts because that container is back at the supplier. So that means you have to have at least some to be able to use in-house, some during production. Then you've got to be able to send some back. They've got to have enough to fill the package, the products into the packaging, and they've got to have enough to ship. So they're going to have the loop. That's where the loop comes in. You've got to have enough for the loop. You've got to have enough for manufacturing. You've got to have enough for assembly. So they've got to keep that circle going. It has to stay full. Trying to think of an example where in life that if you run out of something, you're just kind of, you're stuck. You can't do anything. Brandon, can you think of any examples since you're on?
I wait, hold on.
Okay. Okay, can you hear me now?
It's still like a static noise going on right now. And then, yeah, that got rid of it.
Okay, yes, from my headphones. I won't plug in my mic. Mic alone for now. Okay, so first of all, we know that their work week is 5 days, right? That's your assumption. So if they have a 5-day work week, so you have they need 250 containers per week. They have a 5-day work week. They're using how many, so you want to calculate based on their number of containers per week, and you want to figure out how many they use per day. So if they have 250 containers per week and a 5-day work week, how many containers per day are they using, right? And then you would take the number of containers they're using per day. And that's where you're going to take the fleet size is 400. So your fleet size is 400, and you're basically looking at your number of days. So you're trying to calculate days. So if you have 400 containers, and then you figure out how many containers per day you're using, then once you do that math, it'll tell you how many days, because you're going to take total containers per day, and when you calculate that out, it's going to cancel out containers, and you're going to come out with days when you do the math. Did I clarify that, Brandon, or did I just make that more confusing?
Yeah, it makes sense.
Okay. So yeah, so what you're trying to figure out is how many days of containers you have. So that 400 containers is going to last how many days? Okay, number 7, true or false, and why? If a truck is hauling a trailer filled to capacity, which is cubed out, so we talked about the weighting out, but we know that it's going to cube out if it's not over the weight capacity. It doesn't go past that 45,000 pounds, but you've got it full of, you've got it's full, the whole truck is full. You've got every pallet space filled up. That's when it's cubed out. And you've got bulk bins containing parts that use the cross dock closer to the OEM, not closer to the supplier. So a truck hauling a trailer filled to capacity with bulk bins containing parts uses the cross docks closest to the OEM, not closest to the supplier. So is that true or false? So I would say that we haven't gone to that yet, but that's going to be further in, and you're really just talking about like your loop. So this is an example of your loop. So you've got the supplier, the filled bins or totes. It goes to the assembly plant, and then when they're empty, they get shipped back. So that's a lot of what I'll talk about tomorrow, getting into the loop. Okay, here is your calculation for the fleet size right here. So what you're going to do, you're going to plug in and solve for the unknown. Here's another example of a loop, right? So this one kind of starts talking about your full return containers, or returnable containers here. It's full. If they're shipping, roll packs that are everything, or bins or packs or anything, it's a full truckload. Are they going to need to stop at a cross dock? And if they do, why or why not? Okay, number 8, the assembly plant can elect to receive parts from suppliers either by truck or by rail. The decision is based in part on the travel distance between the supplier and the assembly plant. Okay, so beyond what distance, we've kind of talked about this a little bit, but I don't think we went into complete detail on this yet. This is later in the chapter as well. But what distance in miles does it trigger where the plant says it makes more sense to use rail than on a truck? And, that's going to be further into your reading. So again, we talked a little bit about, how many hours you have, when we talked about the freight rates, they're going to base it on probably the worst case scenario. They're only going to go so far. But in reality, the assumption when the supply chain people are trying to maximize their loads and get the loads to them the fastest, they're going to look at things like having a truck, the drivers limited to how many hours they drive. Maybe they're actually going to have 2 drivers, and you're going to tag team it. It can be a double run, or maybe the truck driver stops and the truck driver changes so that they don't run out of hours. They assume that, they're running 70 miles per hour on the truck. They're going to be on mostly highway. So, think about those things. What are some of the things that would trigger, when it doesn't make sense for a trucker, when it makes more sense for it to be put on a rail car. And again, that's in your reading. Number 9, a supplier estimates that it will need a fleet of 1,000 totes to supply the assembly line with enough parts to continue production without interruption. Again, the supplier, when they estimate this, they're going through that fleet calculation that you'll see in the chapter, and I'll go through that tomorrow as well, but you'll read about that. How many extra totes should they ask the OEM to buy due to anticipated maintenance losses? Okay, so the maintenance losses could be, they get damaged, they get maybe oily and they can't clean them anymore. Maybe hinges break off. They get damaged, with fork trucks running them, hitting them into doors. Maybe they put them outside and they rust if they're racks. Well, this is an example of tote, but maybe they put them outside and they get dirty, and then they, in the wintertime, and then they crack. So just a lot of different reasons why they may not get, they may not, but at the end of the 5 or 7 year period for the program, they are not going. So if they have 1,000 totes, they're not going to have 1,000 when they're done. So they usually try to order something for a buffer. There is a guideline, and you'll read about that. I will tell you, go by what's in here for the guideline, but I will tell you that when you're working in automotive packaging, something to keep track of, because you've got things like theft, you've got damage, just there are many things that can occur. I've found that the attrition rate in how many totes you're going to lose during a program is more than this percentage, but use this percentage as the starting point, and that'll kind of give you an idea. It probably seems like a lot, but I found it's more than that. Okay. But again, for number 9, use the number that is in your reading for your percent for loss. Let's see. Number 10, what is the required safety stock for parts coming from a supplier that is 600 miles from the assembly plant? So this will be in your reading as well. So they will have, things you'll see as you build these fleets and you determine how many you need. You're looking at how much material you need, how much you're running, how much material you need, how much travel time is involved, how much loss you anticipate for breakage or theft, or just things getting lost, people using bins as footrest or whatever they might use them to take them home, they use it for their hobbies or whatever. There's just so many reasons why these containers will end up on the side of the road. If you work in automotive packaging at some point, you will get an email from somebody at your job saying, look what I saw. And they snap the picture of an empty bin with the company name on the side of the road, or someone's using it as a flower bin at their front door or whatever. You'd be amazed. So, but besides that, there's a required safety stock. So when we start talking about the just in time, getting to the plant just in time, there should be a safety stock. So even if the plants are running, they're across the street and they plan to run, every couple of hours, and they say we can change the order up at any time, you give us what we need, there's still a safety stock required that you need to have. So let's say that, you're building where you're building and you're used at your facility, and you're used to, having these things coming every day, so you can build, you've got enough to maybe build 2 or 3 different models for the assembly plant or whoever your customer is upstream, and you're able to manage those changes. But let's say you get a snowstorm, or let's say the truckers go on strike, or whatever may happen, right? The plant shuts down, get COVID, anything. There is some required safety stock that people will have set aside, so that if the plant goes down, I think we saw this when Japan had an earthquake. When the plant shut down, people had safety stock, so that when they started running, everybody shut down. So no one was really looking for vehicles at that time. But when they started up, they were expected to start right up. And the plants that didn't have safety stock, they didn't have this much material set aside, so that when everything started back up, they could just start working. Those are the plants that suffered, the ones that didn't have any safety stock. When they said, okay, everybody go back, everything's safe, you go back into the building and start working, there's no material. So they're shut down for an extra day or 2 days or a week or whatever, because they don't have their reserve. So what is the required safety stock in hours as a general rule for parts that are coming from a supplier that's 600 miles from the assembly plant? So, it's in your reading, keep that in mind. I'm trying to think of what else we can cover. So I think that covers the homework. You know, I'll go over tomorrow. Like I said, I'm going to go through the whole, the fleet calculations and those sorts of things. And I'm going to have even more about the fleet calculations when I go into some detail outside of chapter 4. You'll see a little bit later. But the general fleet calculation that you see is it's pretty standard and basic. It doesn't account for things like peaks, you know, when they have downtime or they have a peak season or anything like that. But those are some things to keep in mind. Or if you have like whip material. So sometimes, you know, you have internal whip. They might keep the blue versus the pink bins in-house, but sometimes the parts coming in, they might, you know, they might make this part here, but then they need to go out to a secondary location or even within the same plant, another building, and they have like another day's worth of processing because maybe now they have to add some widget on it to make that part work. Or that might be an example with like some of these assemblies. Some of these assemblies are built by the supplier. Some of them are kitted, but there might be assemblies where they have to go to maybe 2 different locations in different parts of the country, or just maybe across town or whatever it is. So, you know, those are some things that can affect the fleet size as well. Okay, you see. So tomorrow, I think I went ad nauseum for a lot of this stuff, but tomorrow, you know, we'll go through some of these. This is how to, you know, get a little bit more into your bins as far as alignment and some different ideas for arrangement. I'm probably going to breeze through this though, because in reality, most of the time people want in the assembly area, they don't want to have to manipulate things. They want to pull it out, the same thing every single time. So I'll go through some of this, but and there also are programs that can calculate these. I've never used any of these programs, but you can. Let's see what else. So I'll go through a little bit of these. These are very similar to like Topsy Cape. I'm thinking that some of you all have probably either used it or seen it already. And then we'll go into fleet size tomorrow. And you can see all the things that go into fleet size. And it's really important to know the loop, what your loop is. And this is where I was talking before about if you're using returnables, are you on a train? Are you on a plane? Are you driving? Are you stopping in multiple places? Is there a border crossing? All these things will determine what your fleet size is, because the fleet size is basically the number of days that you have, and then you multiply your containers by that. So, but again, this is your fleet size. Your fleet size calculation is on page 418 of your homework. And this is something that in automotive packaging with returnables, you will be referring to this. This is the base calculator. I have some other ones I'll show you that people do at different companies, but you know, you'll come up with what works for you if you're in automotive packaging. These are some examples again, but we'll go through all this tomorrow. Brandon, any questions before we close?
Nope, I'm all good.
Okay. All right. And you guys, if you have any questions, I know we went through a lot today, a lot of calculations, but it's important to know this, you know, for the homework. We will go through fleet sizing and those sorts of things tomorrow. We'll start on that. And I think that's it. And I look forward to talking to you all again tomorrow. I will not be recording live. I will record it and I will post it tomorrow, probably tomorrow evening. So you'll have it, but I'll try to post it earlier than tomorrow evening, but I guarantee you I will have it by tomorrow evening, Thursday evening at the latest. So thanks, everyone.
All right.